Welcome to this video lecture. Mark Scythian, FAA licensed aerospace technician, airframe, power plant, and avionics certified. Date today is June 23rd, 2016. In this video lecture, we will be discussing how to calculate automobile piston engine brake horsepower, foot-pounds torque, and brake thermal efficiency while the automobile is in motion. This will be a two-part lecture. The first part will cover the formulation and concepts, and the second part of the lecture will carry out the applied calculation to an actual automobile make, model, and year. The car that we will be working with here is the 2012 Chevy Impala. First, we must start with the required specifications to make these calculations. We must know its curb weight in pounds, 3,555 pounds, the aerodynamic drag coefficient, which the manufacturer states is 0.33. The fuel used will be gasoline on a 4-stroke 6-cylinder 3.6 liter displacement automobile piston engine. The gasoline contains 20,000 BTU per pound potential energy at a fuel density of 6 pounds per 1 US gallon. The bore and stroke of the reciprocating piston engine is 3.7 inches in bore diameter of the piston, and the stroke displacement is 3.37 inches. Compression ratio 11.5 to 1. Maximum indicated horsepower of 300 IHP, should be an I, at 6,800 RPM. Maximum torque output in foot-pounds, 262 foot-pounds at 5,300 RPM. Fuel economy highway, 30 miles per gallon at 70 miles per hour with overdrive transmission. Three different types of horsepower to be aware of on any type of engine, motor, or power system. The indicated horsepower is the total horsepower involved with the entire engine, including the power lost to keep the engine running, plus the usable power available at the engine's crankshaft at a given RPM. The brake horsepower is the usable power output at the crankshaft at a certain RPM. The friction horsepower is the power lost to keep the engine running at a certain RPM. The potential energy stored in the fuel, measured in BTU per pound, can also be translated from thermal energy into mechanical energy. The ratio is 1 BTU per minute heat output, or if 1 BTU of thermal energy is released over 1 minute, that equals 17.6 watts of power. 1 horsepower is equal to 746 watts. So the equivalent mechanical energy in the form of burning fuel can be calculated so that the actual brake horsepower, when divided into the fuel consumption and equivalent mechanical energy output, can then yield the efficiency. Brake mean effective pressure. This is the pressure exerted upon the piston during its power stroke, measured in pounds per square inch. BMEP is directly proportional to the brake horsepower and the foot-pounds torque output at the engine's crankshaft. In this case, we are using a 4-stroke gasoline piston engine. 4-stroke duty cycle reciprocating piston engines include downstroke on the air intake cycle. In the case of gasoline, it would be both air and fuel intake, then compression on the upstroke, power on the downstroke, exhaust on the upstroke. That would represent the 4-stroke duty cycle. In this case, we're using a 4-stroke, 6-cylinder, gasoline-powered automobile piston engine. In the case of a 2-stroke engine, like a chainsaw or a string trimmer on power equipment, there is 2 strokes of the piston to 1 duty cycle, a downstroke representing power, air and fuel intake and exhaust, and an upstroke representing compression. But we have to use the 4-stroke VMEP formula to mathematically calculate the pressure on the piston head during each power stroke. That would be equal to the foot-pounds torque reading at a given RPM divided into the cubic inch displacement times 150.8. If there is a 1-to-1 ratio between foot-pounds torque output and cubic inches, then the PSI pressure during each power stroke will be equal to 150.8 PSI. The most accurate way to calculate the brake horsepower of a piston reciprocating engine is to multiply the VMEP in PSI times the stroke length in feet, the stroke of the piston displacement in inches divided into 12, times the piston head area in square inches, which is the bore diameter divided by 2 squared, times pi, 3.14, times the number of power strokes per minute. So on a 4-stroke piston engine, there are 2 revolutions of the crankshaft for every 1 power stroke. On a 2-stroke piston engine, there is 1 revolution of the crankshaft for every power stroke. In this case, since we're using a 4-stroke duty cycle reciprocating piston engine, the power strokes per minute would be equal to the RPM divided into 2. Last is the number of cylinders, K. Once these 4 are multiplied, the product of these 4 values is then divided into 33,000, which is the number of foot-pounds per minute to 1 horsepower. Since we're using RPM, you have to divide this value into the number of foot-pounds per second over a minute. 550 foot-pounds per second times 60 seconds equals 33,000 foot-pounds per minute to 1 horsepower. When you use this formulation, you will mathematically calculate the brake horsepower output of a reciprocating piston engine. Next is finding out the required horsepower to accelerate the vehicle from rest to a given final speed. The most accurate formula to use algebraically would be the power is equal to mass kilograms times final velocity in meters per second, quantity squared, divided by 2 times the time it takes for the acceleration. So converting pounds into kilograms, dividing pounds into 2.2 for kilograms, meters per second is feet per second divided by 3.28 feet to 1 meter, and time in seconds of acceleration. To calculate miles per hour to feet per second, that would be equal to the miles per hour times the fraction of 22 over 15. That will get the feet per second. Then the feet per second divided into 3.28 to get the meters per second. When calculated correctly, the watts power to accelerate the vehicle will be known. That is then divided into 746 watts, which is equal to 1 horsepower. So now you've gone to a final speed after acceleration. Now you're at steady cruise speed, no acceleration, no deceleration. The forces opposing the inertia of the vehicle are only going to be the aerodynamic drag and the tire rolling resistance. If you're going up a hill, you have the sign of the angle of the road, positive or negative. Going up a hill, you have to overcome gravity, so more power. Down a hill, gravity assists you, so less power. But we will assume we're on level road on this particular analysis. So now the next is we're at cruise speed. We want to know what kind of horsepower is required to keep the car at a steady speed. So the only forces on level road opposing the inertia of the vehicle is the aerodynamic drag and the tire rolling resistance. So the formula to calculate the power in watts to overcome aerodynamic drag the engine must provide would be the drag coefficient of the vehicle times the projected frontal area in square feet times the air density and slugs per cubic foot air density times the cruise speed in feet per second cubed divided into 2. That power in watts calculation is then divided into 746 to get the horsepower required to overcome aerodynamic drag. The power in foot-pounds per second to overcome tire rolling resistance is equal to the weight of the vehicle times the speed in feet per second times the coefficient of tire rolling resistance, the CRR. For automobiles and light trucks on dry paved road, that would translate to a coefficient of rolling resistance of 0.012. When multiplied out, the foot-pounds per second power required to overcome tire rolling resistance will be known, which is then divided into 550 foot-pounds per second, which equals 1 horsepower. These two values are then added together, and then that is the total force opposing the inertia of the automobile. The engine must provide that horsepower in order to maintain a steady cruise speed. Uphill and downhill variables are added and subtracted to the sine of the angle of the road in degrees. Since we're going to stick with level paved ground, we will use the previous formulations without respect to angle, positive or negative of the road. So earlier we learned about the potential energy in the fuel. If we calculate the brake horsepower output and divide it into the power input in the form of burning fuel related to horsepower or watts or foot-pounds per second from the BTU per minute equals 17.6 watts formulation, we can find out the efficiency. Also, when you're dealing with liters displacement in the metric system, 1 liter is 1,000 cc. If you want to go from cubic centimeters to cubic inches, you multiply the cc's times 0.061, and that will translate to the cubic inch displacement. That is because it takes 16.387 cubic centimeters to equal 1 cubic inch of volume. This is the end of part 1 of this lecture, explaining the formulation and concepts. In part 2, we are going to start making actual calculations on the 2012 Chevy Impala. This is the end of part 1 of this lecture. please continue on to part 2 of this lecture.